Okay, good morning. So this is our 8th lecture, and today we will specifically talk about the interaction of multi-phase flows with turbulence, and secondly we will start our introduction to the flow regimes. Okay, so we have some idea of turbulence from our single phase flows. Okay, I hope you have some understanding, because majority of you might have taken either course on advanced fluid mechanics, and even whenever we talk about basic fluid mechanics, then some very preliminary details about the turbulence actually we study there. But of course we will also not going to be into very deeper details, but some aspects we will actually try to see. So first of all, we have to understand that if we have turbulence in our system, then what changes will be happening. So number one, if we have turbulence in the system, whenever my particles will be interacting with the turbulent flows or turbulent eddies, then there can be breakup and coalescence of the particles. Is this point clear? So of course, if you have a solid particle, then you will not be experiencing much breakup unless or until forces are very strong. But if you have fluid particles like bubbles or drops, so when bubbles or drops will be interacting with the turbulence, then there will be either a breakup or agglomeration of the particles, agglomeration or coalescence of the particles once we are actually seeing the interaction of the fluid particles with the turbulence. Okay. Second important point is that there can be modification of turbulence. Now, what is the meaning of this modification of turbulence? Okay. So whenever the fluid particles are actually interacting, so for turbulence I am using just TUR. So what do we mean? Whenever fluid particles or any solid particles are actually interacting with the turbulent flows, so of course the particles are having some their relaxation time. Okay, and turbulent eddies are also having some of their time scales. Now, depending upon the relative nature of these time scales, either these particles can reduce the turbulence or these can enhance the turbulence. Okay, so basically if your particles are of very small size, then their hydrodynamic relaxation time will be very small. So in that scenario, whatever the fluctuations particles will be experiencing in the turbulent flow, particles will immediately try to follow the flow. So once particles are actually following the turbulence eddies, in that case what will be happening? Particles are moving with the turbulent eddies, and these are moving only because of the, why these are moving? These are moving only because of the energy supplied by the turbulence. Okay, so in that case particles will actually absorb the energy of the turbulent eddies. So in that scenarios, particles will try to decrease the turbulence. On contrary, if particle sizes are large, then their hydrodynamic relaxation time will be large, and in that scenario we will be finding that particles will not be able to follow the turbulent eddies, and when turbulent eddies will be interacting with the large size particles, there will be strong wake formation, and in the wake formation there will be actually enhancement of the turbulence. Okay, because new eddies will be generating because of the wake behind the particles. So this is something which will be happening when our multi-phase flows will be interacting with the turbulent flows. Okay, so two things, either there can be breakup and agglomeration of the phases, particularly for fluid particles, and there will be modification of turbulence itself. So modification can be in two ways, either there can be enhancement of the turbulence or there can be mitigation of the turbulence. Okay, so now whenever we talk about the turbulence, we see two important quantities. One is called as Kolmogorov length scale, and other is Kolmogorov time scale. Okay, so lambda is nothing but our Kolmogorov length scale, and Kolmogorov time scale is my tau. Okay, so if you see in case of turbulent flows, you might have seen in your basic fluid mechanics also, whenever we introduce the turbulence, then either we show the flow over a flat plate or we show flow through a pipe. Okay, so there if you see the picture of the turbulent flow, then you will be finding in that particular picture, you will be having actually large number of this type of rotating structures, vortices. Some will be of smaller size, some will be of larger size, and their number will also be huge. So your fluid structures will be kind of large number of rotating vortices. Okay, so these particular vortices, or I can say these are specifically called as turbulent eddies. So these turbulent eddies are having actually different sizes. Okay, so some of the turbulent eddies will be having size. Say if this is my pipe, so I can see that if my D is internal diameter of the pipe, then particularly these two eddies which are larger in size, their size or their length scale is almost of the order of the diameter of the pipe. On contrary, some of the eddies are of very small size. So if you talk about this eddy may be of D by 5 size. Okay, so similarly there can be even more smaller eddies. Okay, so typically if you study the turbulence spectrum, you will be finding that when the length of the turbulent eddy increases, its energy content also increases. So it means in any turbulent flow, all the turbulent eddies whose sizes are larger, they are carrying more turbulent energy. Okay, and the eddies which are of smaller size, these are having less turbulent energy. Okay, so particularly whenever we say the term Kolmogorov length scale, Kolmogorov length scale is nothing but size of smallest eddy present in our system. Is this point clear? So as I told you, in a turbulent system, we will not be having eddies of any uniform size or same size, but we will be having wide spectrum of sizes of the eddies, and the eddies which are having smallest size, these are called as the Kolmogorov length scale. And in order to determine the smallest size, we have these two terms. Nu, this is nu. What is nu? Kinematic viscosity. And another term is epsilon. What is epsilon? Epsilon is called as rate of eddy dissipation per unit mass. Okay, or dissipation of turbulent kinetic energy per unit mass. So rate of dissipation of turbulent kinetic energy per unit mass. Okay, so this is my epsilon. Okay, so nu cube by epsilon whole power 1 by 4. If you check the dimensions, these will comes out to be dimensions of a length. So that's why this we are calling as our Kolmogorov length scale. Okay, on contrary, if you simply do kinematic viscosity by epsilon whole power 1 by 2, then I will be getting time scale. So what is the meaning of time scale? The way I told you that we will be having wide spectrum of eddies present in our system, in the similar way we will be having actually wide spectrum of time scales present in the system. So what is the meaning of time scale? As I already told you that these arrows are depicting nothing but the direction of rotation of that particular flow element. Okay, so whenever these turbulent eddies are actually rotating, so some of the eddies are rotating at low velocity, low speed, and some of the eddies are rotating at actually very high speed. Okay, so now depending upon their speed, we can define the time scale. So all the eddies which are rotating at high speed, we can call these as nothing but fast turbulent eddies. Okay, so tau represents the Kolmogorov time scale, which is nothing but fastest time scale of the fastest turbulent eddy. Is this point clear? So whenever we are talking about the length scale, we are trying to go for the smallest one, and whenever we are talking about the time scale, we are trying to capture the fastest eddy. Why? Because if I keep my time as small as possible to that of the fastest eddy, then of course all the eddies which are having time scale larger than that, these will be captured well automatically if I am able to capture the fastest eddy in the system. In a similar way, if I am able to capture the smallest eddy present in the system, then all other turbulent eddies which are larger than that, I will be able to capture these. Okay, so that's why if say whenever we talk about like direct numerical simulations of the turbulent flows, DNS. So in case of DNS, our idea is to capture each and every turbulent eddy present in the system. So whenever we perform the direct numerical simulations, then our mesh size should be equivalent or smaller in comparison to the Kolmogorov length scale, because then only we will be able to capture the smallest eddy. And our time step, so whenever we proceed a transient solution, so we are having solution known at the initial step, and then we march our solution through some time step delta t. So our delta t should be smaller than the time scale of the fastest eddy. Then only we will be able to properly capture it in the time. Okay, is this point clear? So all are clear up to this? So this is, till now we have not done anything about the interaction of multi-phase flow with turbulence. Till now I have given you the very basic idea of only turbulence. Okay, now let us talk about another scale. So here epsilon, which is nothing but rate of dissipation of turbulent kinetic energy per unit mass, it is of order of u cube by L, where u is nothing but your reference flow velocity and L is nothing but your reference flow time scale, reference flow length scale. Okay, is this point clear? So characteristic length of the flow, and if I consider the reference velocity of the flow u cube by L, that is nothing but our formulation of the dissipation term. So now I can replace this dissipation term in my length scale and time scale with u cube by L. Okay, so if I do so, then I will be getting one quantity that dimensionless Kolmogorov length scale is nothing but equal to Reynolds number power minus 3 by 4. Okay, and Reynolds number is nothing but u into L by nu. Okay, so Reynolds number formulation over here is nothing but u into L by nu. Okay, so that is my Reynolds number. So you can see that the Kolmogorov length scale is nothing but equal to Reynolds number power minus 3 by 4, and similarly you can see u tau by L is proportional to Re power minus 1 by 2. So one very simple conclusion in case of turbulence we can make: as my Reynolds number of the flow is increasing, so this is nothing but inversely proportional to Reynolds number power 3 by 4. So as the Reynolds number of the flow is increasing, my length scale will keep on decreasing. As Reynolds number is increasing, again time scale is also decreasing. It means my turbulent eddies are becoming more and more faster and more smaller. Okay, so that is the reason whenever we talk about direct numerical simulations, so in terms of direct numerical simulations, data is available only for moderate range of Reynolds numbers. So if you search any data set available in the literature or provided by different sources, you will be finding that DNS data of turbulence is not available for high Reynolds numbers. Okay, so data is available only for low to moderate Reynolds number conditions, particularly in the turbulent regime. Because upon increasing the Reynolds number, the requirement of achieving the length and time scales are decreasing. So because of that, one has to employ more and more computational resources. Even with the present day high speed computers, we cannot go up to very high Reynolds number, because then also simulations will take years to, direct numerical simulations will take years to give us the output. Okay, so this is the whole conclusion, that once the Reynolds number increases, our turbulent length scale and time scale of the turbulent eddies decreases significantly, which actually increases the complexity in capturing these length and time scales. Okay. Now, there is one interesting graph. This particular graph is given in terms of change in turbulent intensity. So this change in turbulent intensity is given in percentage, and then ratio of particle diameter to turbulent length scale. So it means in this particular graph now we are trying to see the interaction of multi-phase flow particles with the turbulence. Okay, so first thing is, here we have actually talked about only spherical particles. Say d is the diameter of the spherical particle. Okay, then in the left hand, in this abscissa, they have considered this abscissa axis as ratio of particle diameter to turbulent length scale. So it means d by lt. So where lt is nothing but turbulent length scale. Now, just now I told you that in any system we will be having large number of turbulent length scales present in the system. Okay, so how we will be deciding that which of this length scale should be my LT? How we can decide? Can you tell me? I have given you some hint before this discussion. No. So I told you that in case of turbulent spectrum, energy spectrum of the turbulence, larger eddies carries the more energy and smaller eddies carries the less energy. Okay, so, and I also told you that if my particles relaxation times are smaller in comparison to the turbulence time scales, then particles will try to follow the turbulence eddies. Okay, and in case of turbulence also, the smaller eddies are actually driven by larger eddies only. So particularly larger eddies are the ones which carries the energy from the mean shear flow, and then these larger eddies transfer that energy to the smaller eddies. Basically in turbulence also, smaller eddies are nothing but the sources of energy dissipation. So all the dissipation in case of turbulence is because of the smaller eddies only. Larger eddies are actually carriers of the energies which carries the energy from the mean flow, and there is almost negligible dissipation of energy in case of the larger eddies. So that's why if particles will try to follow the turbulent flow profile, majority of that energy is nothing but coming from the large eddies only. So whenever we will be deciding this turbulent length scale, we will be considering this to be equal to the length of largest eddy. Is this point clear? All are clear with this point? So whenever we are selecting this LT, this is nothing but we are talking about the length of the largest turbulent eddy present in the system.
So ये तो characteristic length ही होगा.
Yes, this is nothing but characteristic length of the flow. Okay, so d by lt I have plotted along this side, where d is my particle diameter, and then in the ordinate axis I am having change in turbulent intensity. So it means turbulent intensity for flow with particle minus turbulent intensity for flow without particle divided by turbulent intensity for flow without particle times 100. Okay, so that is the relative change actually we are trying to see. So one interesting thing is, when ratio of d by lt is small, okay, when ratio of, so this is the portion you can see up to this point, almost up to this point, or I can divide this curve into three categories. So you can see one is this category. So particularly in this regime, ratio of d by lt is very, very small. It means my particle sizes are very small in comparison to the characteristic length scale of the turbulence. So when particle sizes are small, their relaxation time will also be small. And once its relaxation time is very small, it will immediately try to follow the changes which are happening in the turbulent length scale. Okay, so it means particles will try to completely follow the turbulent eddies. So once the particles are following the turbulent eddies, it means turbulent eddies are investing certain amount of energy in order to push these particles. So that's why there will be loss of energy of the turbulence. So that's why you can see that turbulence intensity is actually in the negative direction. Okay. Here also, in this region also, in majority portion, the turbulence intensity is in the change in turbulent intensity is in the negative direction. But on contrary, when the particle sizes have become larger, then particles will not be able to follow the turbulence. Once particles are not able to follow the turbulence, their response time is larger in comparison to the motion of the turbulence. So particle will remain there itself and turbulent eddies will just bypass it. So once the turbulent eddy is bypassing it, so there will be formation of more wakes and more number of turbulent eddies. New turbulent eddy formation will be happening, which will lead to increase in turbulence. So it means that if you have some particles which are of larger size present in the system, then these results in enhancement of the turbulence. Is this one clear? So that is something which we can conclude from this figure. Okay, all are clear with this idea? Now, of course, I have given you this idea in terms of the
एनर्जी लॉस तो उसमें भी होगा सर.
yes, but of course they are receiving the more energy from the mean flow. So in this case, energy loss is there, but this rate of viscous dissipation is less in comparison to the rate at which they are receiving energy from the mean flow. So that's why there is enhancement of the turbulence. Okay. Now, I simply told you at the moment that we can consider this in terms of the relaxation time divided by the time of the turbulent eddies. Okay, because all the particles which will follow, these will be having relaxation time lesser in comparison to the time scale of the turbulent eddy. Okay, so now we can present this idea in terms of a non-dimensional number, which is called as Stokes number. So here you can see MP divided by 6 pi mu r. What is this? What is this 6 pi r mu? This is nothing but our relaxation time. Okay. So if I take the ratio of relaxation time divided by tau, what is tau? Kolmogorov time scale. So Stokes number is nothing but T mu by tau. So relaxation time by this turbulent time scale. Okay. So now if value of ST is very small than 1, in that case for any flow, if my Stokes number is very small than 1, in that particular flow I can say that turbulence will always result in this interaction of particles with turbulence will always result in decrease of turbulence. Okay. On contrary, if my Stokes number is unity or greater than 1, greater than nearly equal to 1, or even greater than 1, in both these scenarios, interaction of particles with turbulence will lead to enhancement of turbulence. Is this one clear? Okay, now one interesting fact. So till now, whenever we talked about the interaction of particles with turbulence, we only considered size of the particle as parameter. Okay, but of course there can be other different conditions such as density of the particle. Okay, then there can be other condition as mass fraction of particles. So if say very few number of particles are present in the system, or if say in my fluid there is large concentration of particles present, then what will be happening? Okay, so to see these effects here, the mass fraction of the particles is actually plotted along abscissa, and along the ordinate we have changes in turbulent intensity. So of course these percentage changes are separately given for turbulent kinetic energy and rate of dissipation. So you can see that if this is when you are having the mass fraction 0.1, then your turbulent kinetic energy has decreased and rate of dissipation has also decreased. But when mass fraction you are keeping on increasing, then actually there is further decrease in the turbulent kinetic energy and rate of dissipation. And consider this particular graph is given for d by L tau, when d by L tau is actually small. So it means this is in the regime where automatically our turbulence will be decreasing upon interaction with the particle. So that's why all the data points you are finding are below 100%. Is this one clear? So it means that whenever we will be having increase in mass fraction of the particles, then that will lead to further decrease in turbulent kinetic energy and rate of dissipation. Okay. Now this is one interesting photograph. So here in this particular photograph you can see these white spots. So these white spots are nothing but locations of particles. Okay, and then you have these black colored points, black colored holes in between the particles. So these are nothing but the turbulent eddies. So this is photograph of a channel flow. So flow is happening from left to right through a channel, and the flow inside the channel is nothing but a turbulent flow. Okay, and in this turbulent flow there is smaller dust particles are actually loaded. So here you can see whenever you will be having rotation, so we have seen in case of even centrifugal separators. So if you talk about centrifugal separators, there what happens? Your flow is rotating, and if you put any solid particles which are of heavier weight, these solid particles, because of the centrifugal acceleration, they will try to move in the outward direction. So here you can see that all these are nothing but turbulent eddies, and in these turbulent eddies actually all the particles are trying to collect at the outer portions. Okay, and if this is one turbulent eddy, there will be some other turbulent eddy here also. So it means particles are getting collected at the high shear zones. When you have interaction between the two turbulent eddies, then one may be moving in any direction, other is moving in any random direction. So in between the two there will be highest shear. Okay, so this photograph represents that all the solid particles are actually being collected. When the size of the particles is larger, then these particles are not following the turbulent eddy, but these are getting collected towards the high shear zones. On contrary, if you consider the lighter particles, like if in this particular flow only, in place of solid particles, heavy solid particles, if you disperse small bubbles, if you consider this is the flow of a liquid and then you are adding small air bubbles into that, then we know that lighter phase gets collected at the center. Okay, so if you see vortex formation, in vortex formation, when air enters into the free surface, then air profile, air amount is actually holded at the center, and then liquid is getting outside. So this is all the effect of centripetal or centrifugal acceleration, which will also come into picture once particle sizes are becoming heavier. Okay, heavier or lighter, it means density ratio is large. So there are few conclusions which we have to make. Of course, one simple idea also let me give you. So this turbulent length scale is also very interesting to determine that how to decide which eddy is largest and what is their largest size. So typically whenever we talk about the pipe flow, for pipe flow largest length scale of the turbulent eddy is considered almost 0.2 to 0.3 times of the internal diameter of the pipe. Is this point clear? So for channel flows, if you have to decide LT, so typically you can consider around 0.2 to 0.3 times of its internal diameter. Okay. So now all these points I think I have written in text to summarize. So if TU, which is nothing but the particle relaxation time, is small compared with L by U. L by U is nothing but, this is time scale of the characteristic time scale of the flow. So if my particle relaxation time is small in comparison to characteristic time scale of the flow, then dust particles will be destabilizing the, is small compared with L by U. Yes, then dust particles will be destabilizing the flow. If TU is greater than characteristic time scale, then it will be stabilizing the flow. So here reverse is happening in case of dust particle. Why? Because when you put the dust particle, these will either, in first case what will be happening, when T mu is small, their relaxation time is small, so it means these will be responding fast, and because of the fast response, these will try to move towards the outer direction. Okay, so that's why this will destabilize the flow. On contrary, if this is larger, then these will try to stabilize the flow. Okay. So your response time is very fast. If response time is very fast in comparison to the mean flow, so whatever the smallest fluctuation is happening in the flow, these particles will respond to that smallest fluctuation as well. So these will not follow the mean flow, rather these will follow the small turbulent eddies. So here I am not referring to the, I am not saying that I am talking about turbulent intensity. I am talking about the flow stability. So flow stability means if my mean flow is happening from left to right and all the particles are kind of completely following the mean flow, then I will be calling it as a stable flow. But if my particles, in place of following the mean flow, these are trying to accumulate near the turbulent eddies, then I will be calling it as unstable or destabilized flow. Okay, so that is the reason I am calling that if my T mu is small, then of course instead of the characteristic mean flow, particles will respond to each and every turbulent fluctuation present in the flow, so these will destabilize the flow. On contrary, if this is larger than the mean time scale, then particles will mainly try to follow the mean flow and it will lead to a stable situation. Again, one very interesting phenomenon comes particularly in case of bubbles. So in case of bubbles, what happens? Bubbles are containing air inside that. Okay, and the primary nature of the air is that it is a compressible substance. It can be easily compressed. Okay, if it experiences higher pressure, etc., so it can be easily compressed. So typically you will be experiencing that if you are having liquid as your continuous phase and bubbles are moving inside that liquid, then depending upon the surrounding pressure oscillations or surrounding flow oscillations, you will find that there are shape oscillations in the bubble. Okay, so it means that at some point of time bubble may be of this shape, at some point of time bubble may become this shape, at certain point this may become this shape, and then it may become this shape. Okay, so all these are nothing but shape oscillations in the bubble. Okay, so if we try to find out the omega m is nothing but frequency of these shape oscillations, and omega n is natural frequency of the bubble. So if ratio of these shape oscillations or fluctuations in the bubble shape divided by its natural frequency is very small than 1, then primary effect of the bubble is to increase the effective compressibility of the fluid. And if you have more compressibility, it means you have more capacity to absorb the shock and energy. Okay, so that is the reason increased compressibility causes increased stability of the bubble. and bubbles present in the system will try to stabilize the flow. Is this point clear? So what I am trying to say, that if oscillation frequency of the bubbles is smaller in comparison to their natural frequency, then the response of the bubble to oscillations will be fast in comparison to its natural response to regain its shape. So in that scenario, overall effect is we will be experiencing the enhanced compressibility of the fluid. Okay. Once we are experiencing the enhanced compressibility, it means it will have more tendency to absorb the outer fluctuation. So that's why it will actually try to stabilize the flow. Okay. So you can see that when we are near resonance or at resonance,
means bubble try to collapse continuously.
yes, bubble is not trying to collapse, but bubble is trying to compress, yes, decrease in its volume. So when there are when we are close to the resonance, then there are bands of frequencies in which flow is less stable and bubbles are therefore destabilizing. Okay. So if compressing frequency matches with the natural frequency, we know that what will happen? Resonance. So resonance will try to amplify the frequencies. So if it is trying to amplify the frequency, you will see significant surface curvatures and significant oscillations in the bubbles. Okay. So because of that, overall effect will be that it will try to destabilize the flow. It will try to create periodic oscillations in the surrounding phase as well. So these periodic oscillations in the surrounding phase will nothing but destabilize the flow. Okay.
So ये bands of frequency का क्या मतलब है?
Bands of frequency means at resonance or near resonance, you will not be having any single value of omega n by omega n at which this effect is amplifying. You will be having a number of frequencies available. So that number of frequencies, if we are collecting together, then we are calling that as frequency band. Okay. So it means that when the response time of the particles or bubbles, both the relaxation time and the natural period of volume oscillation. So it means if you talk about solid particles, in case of solid particles, there will be competition only between the characteristic mean time of the flow and relaxation time. But when you will be talking about the fluid particles, then in case of fluid particles, in addition to their response to the continuous phase or mean flow, it means relaxation time, in addition to that, there will be shape oscillations also. Okay, so that's why whenever we will be comparing the fluid particles along with the relaxation time, we have to also consider the natural period of volume oscillations. So their joint effect will be compared with the mean characteristic time. So that's why when both relaxation time and natural period of bubble oscillations, so that is the overall response time. So when overall response time are small compared with the times associated with the fluid motion, then particles simply alter the effective properties such as effective density, viscosity and compressibility. So if your effective density, viscosity and compressibility are being altered, it means these are being increased, then what will be happening? Ultimately your Reynolds number of the combined flow and Mach number of the combined flow is being altered. Okay, so it means that if you simply calculate the Reynolds number and the Mach number of the combined flow, based on their altered value only, you will be able to predict the flow behavior. Is this point clear? What I am trying to say? So when these both time scales, it means overall response time is small, then we will be experiencing that the compressibility is changed. If compressibility is changed, with that other properties such as density, viscosity are also changed. So if these properties are changed, ultimately for overall flow behavior, the Reynolds number and Mach number are changed. Okay, so if I consider combined flow together, then my Reynolds number and Mach number will be actually changing the flow characteristics. So whatever effect on the turbulence will be coming, that will be now based on the effective Reynolds and Mach numbers. Okay. So under these circumstances, the stability is completely governed by effective Reynolds and Mach numbers. Okay. So this is a typical calculation. If you see that you have rho s as the density of the solid particle and rho g as density of the gas particle, then this will be your mixture density for given volume fraction alpha. Is this point clear? Or I can say that this is the enhancement in the density. In other words, because this is not exactly equal to mixture density, but this is the effective density for a effective density change. Okay. Similarly, this is change in viscosity. So how much change in viscosity will be happening? That is actually given 1 plus 2.5 into alpha. So if this is the change in density, this is the change in viscosity, then what will be change in Reynolds number? Because Reynolds number is rho Vd by mu, so change in density will be getting multiplied in the numerator. In the denominator, I will be having this term 1 plus alpha. So it means that I can simply say that my effective Reynolds number will be equal to this whole term, say this whole ratio is say some constant k, so k times of Reynolds number of the normal gas. If gas is my continuous phase without any particles, then Re gas will be my normal Reynolds number. But if in this gas I have loaded the solid particles, so these solid particles have actually, if alpha fraction is added, this alpha fraction has changed my density and viscosity, so my Reynolds number has changed by this multiplier k. Okay, so now if I have to predict the turbulence properties, turbulent length scales, turbulent time scales, then I will be using effective Reynolds number despite of Reynolds number of the gas. Is this point clear?
You solid in the gas.
Yes. Now we can consider the other phase. If my response times are, response times, it means it is including both, because when I am referring to the particle means it can be solid particle, it can be gas particle. So that's why whenever I am referring to response time, it means response time is, I am talking about the both means relaxation time as well as change in volume. So when the overall response times are comparable with or greater than the typical times of the fluid motion, the particles will not follow the motions of the continuous phase. Okay. Of course, if that is there, it is larger, so particle is taking more time to respond in comparison to the fluctuations happening in the flow. Okay, so in this scenario we will be finding that disturbance is caused by relative motion. So if particle is not able to follow the flow, there will be relative motion between the particle and the continuous phase. So the disturbances which are caused by relative motion will tend to generate unsteady motions and promote instability in the continuous phase. Okay.
Solid particle में the volume changes आएंगे.
Solid particle में no. So if your particles are rigid, then it will not be. But if you have say some jelly particle, flexible particle, then there can be volume change.
और सर उस केस के अंदर जब हम टाइम स्केल बढ़ा रहे तब स्टेबलाइज हो रहा था फ्लो.
When
Solid in a fluid.
whenever solid is in a
Fluid.
okay, solid in a fluid means you are saying whenever we are increasing the
टाइम स्केल तो स्टेबलाइज हो रहा था.
relaxation time scale.
Yes, yes.
let me go back. Which point you are saying? This point.
फर्स्ट पे
First, yes, yes. So there it is actually trying to destabilize the flow.
जब घटा रहे हैं तो,
Yes.
और यहाँ पे उल्टा हो रहा है.
No. This is one. This second point, I think you see, this is a typo. Okay, so this is a typo. Please make it correct. If T mu is small, let me again explain this point. So if your particle response time is small in comparison to the mean characteristic time of the flow, then particle will try to follow the flow and we will be having, okay, and when it is, then it will be destabilized. So this may be a, I think, typo.
मतलब सर टाइम स्केल कम हो रहा है तो स्पीड बढ़ेगी ना.
Yes.
So
No, what I am trying to say is, if your particle is not able to follow the mean flow, then it will try to destabilize the flow. But if your particle is following the mean flow, then it will stabilize the flow. And when particle will follow the mean flow, particle will only follow the mean flow if its response time is smaller in comparison to the mean characteristic time of the flow. Okay, so if say this point is, I think, having some typo over here, so this should be destabilize and stabilize. Point is clear?
वो लेंथ पे भी तो डिपेंड करेगा, मतलब कितनी length.
Yes, so that is why, but length we have a unique number, because when we are talking about the characteristic time of the mean flow, then we have LT. LT means length of the largest turbulent eddy, which is a fixed number for a particular type
LT
of.
चेंज नहीं होता होगा, LT
Sorry?
कैरेक्टरिस्टिक लेंथ चेंज नहीं होता होगा.
Of course, LT means length of largest turbulent eddy will be a lot of fluctuating parameter. But what we try to do, whole turbulence estimation is nothing but on approximate basis. So whenever we do it on approximate basis, in case of approximate parameters, we consider it close to 0.2 to 0.3 times of diameter. Okay, so that is for a channel flow. Now if in place of channel flow you go to some other situation, say you have a flow coming out of a jet, there your length of the turbulent eddy will be something different, and it will depend upon the location at the outlet of the nozzle at which you are actually trying to calculate the interaction.
पाइप में अगर देखें तो LT चेंज नहीं होता होगा. अगर बड़े पाइप में फ्लो करेगा तो एडी की साइज बढ़ेगी तो LT चेंज होगा.
Of course, so that's why what I told you, that LT is of the order of 0.2 to 0.3 times of diameter. So it means your diameter of the pipe is increasing, so your LT is also increasing. Are you clear with this point?
Effective diameter.
Yes, of course. If you have a non-circular geometry, then you will be talking about hydraulic diameter. Is this point clear? So please make this correction if I have explained this otherwise, because this I think seems a typo here. Okay. Okay, now.
सर एक बार वो पिछला पॉइंट बता दो.
Okay. Yes. So what we said, that if response times are comparable or greater than the times associated with the fluid motions, the particles will not follow the motion of the continuous phase. That is correct. So if relaxation time of the particle is greater than characteristic time of the mean flow, then my mean flow will move at faster pace, but particle will not be able to follow the mean flow. Okay, and under these scenarios, whatever the relative velocity we will be having, of course, if say continuous phase is moving at certain pace, but particle is not able to follow that one, so what we will be having? We will be having some relative velocity between the two, and whatever that relative velocity we will be having, that will generate unsteady motions and instability. Is this point clear? So please, if I explained this earlier point the other way, make it correct. I think this is a typo. Okay, so this should be stabilized and this should be destabilized. Okay, now this is all about. We will not discuss anything further on turbulence interaction of multiphase flows in the course. Of course, if small discussion is coming in the specific cases, that part only we will take up, but we will not having any detailed mathematical analysis beyond this, because turbulence itself is a complex thing. Multiphase flow is again complex. So without the fundamental knowledge of multiphase flow, we cannot enter into this topic. Okay, so that's why I have just tried to give you the prelude of the turbulence interaction with multiphase flows. Now, whatever the equations of motions we have studied till point, all these equations of motions we studied in two ways. One, we tried to give you the individual phase equations, and second is combined phase equations. So you have to understand this point. Whenever I will be using the combined phase equations for any of my physical situation, then I am referring to the combined system with averaged properties. I am not interested in each and every specific details of the phase distribution or phase dispersion present in the system. On contrary, whenever we talked about the individual phase momentum equations, in terms of individual phase momentum equations, we have referred to the individual phase details, and then we tried to see that from one phase to other phase, what are the forces coming. Okay, until now I have defined you 3-4 interaction terms. One was IN, mass interaction term, second was energy interaction term, and third was this force interaction terms. Okay, so I have simply written that IN, FD and epsilon, and or say QIN or WIN. Okay, but we have not determined their exact value, like what is their magnitude. Okay, so basically the exact magnitude of these parameters is something which is very strongly dependent upon different situations. For example, if flow is happening through a horizontal pipe, then your phase distribution may be something different under the same set of volumetric flux of the two phases. If it is in an inclined pipe, if it is in an vertical pipe, if it is in circular pipe or square duct, so it means this will be dependent upon larger number of flow parameters. At the same point of time, you can change your viscosity, you can change your density, etc. So unless or until we have the idea of estimate of this flow distribution or flow pattern present in the system, we cannot actually determine their exact value. And till now, whatever the values we have determined, these are also not very exact, but these are all actually approximate values. Okay, so before going into that spectrum, which is nothing but on flow pattern, one small idea I also want to give you about some of the averagings which we have done or which we are doing when we are actually calculating the different governing equations. Okay, so if you recall, whenever we derived the governing equations, we were having two conditions. One was d, which was the particle diameter, and second condition was epsilon. And please, this epsilon does not relate it to turbulence. This was epsilon was nothing but the volume of the or dimension of the control volume which we have considered. Okay, and at that time we found that this, what I told you, that my control volume should be so large in size such that it is containing finite number of particles present in it. So it means if d is my size of the particle, then this ratio of d by epsilon was small. Is this one clear? If it is containing larger number of particles in it, then ratio of d by epsilon will be small. Okay. Now, in the scenarios, if you don't have any control on ratio of d by epsilon, it may happen that your d by epsilon is becoming large. So if d by epsilon become large, then how it introduces errors into our system, that is something which briefly I will talk about, not in very detail, but in very brief way I will just explain to you. Okay, so whenever we do averaging, this is one of the averaging formulation I have applied, where we have calculated the QC. QC is any property. If I take the volumetric averaging of this QC property for a continuous phase, then I am writing it 1 by volume of continuous phase and its integration over the entire continuous phase. So this is nothing but a volume averaged value of QC for this continuous phase. In the similar sense, I can also calculate the averaging of this QC based on the total volume. Okay, so here whenever I am referring to VC, it means in my control volume, I am only talking about, if say this is my fraction of VC, this is VD and total is V. So firstly I have calculated the average only based on the continuous phase. Now I am calculating average based on the whole domain, but here because QC is present only in which portion? Continuous phase. That's why I am doing volumetric integral only over the VC. Okay. Now if I multiply this parameter with VC and divide with VC, so I will be getting VC by V. VC by V is nothing but alpha C, volume fraction, times average based on the continuous phase. Okay. So this is one simple representation. It means whatever my average is based on the total volume, that I can simply write volume fraction into average based on the individual phase. Okay, this type of formulation is working very well over here, but whenever we will be talking about the different derivative terms, okay, so there, because all our governing equations are nothing but based on the differential equations, so we are having derivative terms either in space or either in time. Okay, so if I define an averaged quantity within the control volume and if I take the derivative of that averaged quantity, okay, and in other way if I do the second situation, means whatever the variation of individual property is there within the system, first if I take its derivative and then I calculate the average of all derivatives. So we will be finding that average of derivatives and derivative of averages will be same only if d by epsilon is small. If d by epsilon is large, then average of derivatives and derivative of averages for a control volume will not be same. Okay. So how these two parameters will be related, that is something which I have shown you over here. We are not going into mathematical details, but just a point that if you calculate the derivative first, so derivative of QC by del xi, and then you take the average of all these derivatives. And in second sense, first if you calculate QC bar average and then if you take its derivative, then you have to consider this additional term over here which will be actually linking these two. So this additional term is nothing but 1 by volume integral, surface integral of the dispersed phase. So QC Ni into ds. Ni is nothing but normal vector from the surface. Is this point clear?
और ये zero हो जाएगा जब d
Yes. When if you see this particular whole term, the order of this particular whole term will be nothing but d by epsilon square. Okay, order of this whole term will be d by epsilon square. So if it is d by epsilon square, it means when d by epsilon is small, then this quantity will be equal to 0, and when d by epsilon is large, then this quantity will be okay. When I take time derivative, if I take time derivative, and if I consider that all my particles are rigid, it means particles do not have relative motion between them. Okay, so within the particle there is no relative, particles will have relative motion between them, multiple particles, but there is no relative motion within the particle. Okay, so it means if you talk about a solid particle, so if you have a rigid solid particle, then when it is at this location, if I take any point with reference to its center of gravity, then if I now see any other orientation of this, then with reference to center of gravity, again the particle distance at each and every point will be same. So in this scenario, if I do the time derivative of averages and time derivative of average, that will be equal.
Property same, right?
Yes, but if you have a flexible particle, a fluid particle, where particle is not fully rigid, okay, so particles are having some relative motion, and how that relative motion is determined, say if this is the centroid of the particle and this is position of any point, and Ri is position vector of this. Okay, so the rate with which Ri is changing, if I do Qc into dRi by dt times ds and then 1 by volume, so this will be coming as additional correction term in order to calculate these derivatives. Okay, is this point clear?
Yes.
So this is a very brief discussion about averages. Why I want to tell you, because even when we take the combined phase equation, we write in combined phase equation summation over the n, rho n alpha n into Vn, and then rho n alpha n we simply substitute equal to rho, mixture density. Okay, so that is also not a full-fledged solution. That is also nothing but a approximation. Okay, so of course these approximations we have to keep in mind that what are the assumptions under which these approximations are actually behaving well. Okay, so the whole idea is that these approximations are behaving well when our d by epsilon is small. If d by epsilon is small, then all the derivatives what we have written, if we take their average, then these will be equal to derivative of average properties. Okay, so and if d by epsilon is large, then this will not be applicable. Now after this, very interesting part is, or very important part is, in case of two fluid or separated flow modeling. Two fluid or separated flow modeling means we will be talking about individual phase equations. So if we have to apply the individual phase equations to know the correct distribution of the phases present in the system, then we should know the correct estimate of interaction terms. And in order to determine the correct estimate of interaction terms, we have to go into the flow patterns or flow regime maps. We have to understand that first from visual inspections, that under what set of flow conditions how my flow patterns, flow distributions are happening, means in what scenario of flow rates of two fluids I have bubbly flow, I have some other flow conditions called as annular flow, I have some other flow conditions called as stratified flow. Because once I know these visual inspection of the phases, based on that only I will be able to define the interaction terms properly. Okay, so that is the topic which we will be starting from the next lecture, and this topic for the initial 1 or 2 lectures, this will be purely based on the visual inspection. So that's why purely qualitative, there will not be much mathematics. Of course, when we talk about the transformation from one regime to other regime, then there is mathematical analysis across the boundary which defines the growth of stability, growth of instability. So that is something which will try to take up in very summarized way, not in much detail. Okay, so that's all for today.